Now let's move on to the next section, which is the vehicle tractive effort and resistance. What is tractive effort? This is actually the force available at the roadway to perform work. So it's actually the force that comes from the vehicle and it transferred to the wheels. Now the resistance is the force impeding the vehicle in motion. Both of these forces are expressed in terms of newtons. Now let's look at this figure here. This is the figure that shows the forces acting on the road. This is the surface of the road, and as you can see here, this is the vehicle, and the road is actually at an angle of grade in degrees theta g. So you can see some forces that are acting on the vehicle and the resistance forces. If this is the centroid of the vehicle, the weight is here, and we have the resistance forces, which is RA, and the MA, the same direction, and then the RRLF, the RRLR, and the RRLF. RA here is the aerodynamics resistance. RR here is, with the subscript LF, is the rolling resistance of the front tires. And this RRLR here is the rolling resistance of the rear tiles. This is the rear tiles. And then MA here is the product of the vehicle mass in kilograms and the acceleration in meters per second squared. Now, on the opposite direction, we have FF and FR. What are these? This FF is the available tractive effort of the front tires, and FR here is the available tractive effort of the rear tiles. And of course, we have the weight of the vehicle here in newtons. Okay, so if you're going to sum up the forces acting on the road here, we can see that we have the basic equation of vehicle in motion. So the summation of the forces on one direction should be equal to the summation of the forces going the opposite direction. So the FF plus FR here should be equal to the sum of the other forces, which is MA plus the aerodynamic resistance plus the rolling resistance according to the rear wheel and the front wheel, plus there's an RG here, which is the grade resistance that is equal to the weight of the vehicle times sine of theta g here. Now, for demonstration purposes, it is convenient to let the following expression be the FF plus FR. Let's designate it as F, and the rolling resistance from the rear wheel and from the front wheel, let's designate as the total rolling resistance, RRL. Therefore, equation 5.1 from the previous slides becomes F is equal to MA plus RR plus RL plus RG. So the total forces acting on the road should be equal to the resisting forces. This F here is related to the force, the vehicle tractive effort, and then these are the resistance forces. So let's look in detail what are the resistance forces. The first one is the aerodynamic resistance, RA. As we can see in this figure, you can see the wind that is acting against the vehicle. If you've experienced opening the vehicle while it is speeding up, you can feel the force from outside, right? And it creates a sound. So the faster the vehicle runs, the stronger will that force be. And this is actually the aerodynamic resistance. So this resistance comes from three of these sources. 85% of the aerodynamic resistance comes from the flow of air around the body of the vehicle, and this depends on the shape of the vehicle. And about 12% of the RA is coming from the friction of the air over the body of the vehicle. And about 3% comes from the airflow through the vehicle components such as radiators and vents. Now, how do we compute the aerodynamic resistance, RA? We have here the formula. RA is equal to the air density over 2 times the drag coefficient CD times the frontal area of the vehicle in square meters and the square of the speed of the vehicle in meters per second. So take note of this formula in determining the aerodynamic resistance RA. For the density, the rho, the values of the rho, we have the table here, 5.1, which shows the typical values of the air density under atmospheric conditions. So notice here that you have the altitude from a level or ground level road with a road on a higher altitude, 1,500 meters, to higher altitude of 3,000 meters. And also notice that while the altitude is going up, the higher the altitude, the lower the temperature. For example, Baguio, it's located at a high altitude area, so it's colder. Okay, and notice these are the corresponding air densities according to the altitude. So notice that as the altitude increases, the air density decreases. For the drag coefficient CD, we also have typical values depending on the vehicle type. So the first one is automobile or the passenger car, which has a drag coefficient of ranging from 0.25 to 0.55. And it goes up as you have a bigger size of a vehicle. And then a motorcycle has a range of 0.27 to 1.8. Okay, now, what is the power required to overcome the aerodynamic resistance? The power is actually equal to the RA itself multiplied by the speed. So note that the power is defined as the product of the force and the speed. Next is the rolling resistance, RRL. This is the resistance generated from a vehicle's internal mechanical friction and pneumatic tires and their interaction with the roadway surface, as you can see here. So the RR is actually exerted, is between the force between the tire and the road surface. So this is higher the rolling resistance is higher on a low quality pavement such as a rough road. And this increases when you have more or higher vehicle speed. Now, how do we determine the rolling resistance? We have this formula here is actually the product of the coefficient of the RRL, the rolling resistance, times the weight of the vehicle. F here can be determined using this formula, which is a function of the vehicle speed V in meters per second. Now, the power required to overcome the rolling resistance is to multiply the previous equation by the speed V, which yields what you can see in equation 5.9. The next resistance is the grade resistance, Rg. This is the gravitational force acting on the vehicle. Now, as previously mentioned, Rg is equal to the weight of the vehicle times the sine of the theta g. But sine theta g is approximately equal to the tangent of the theta g because it's assumed that it's very small. So if we substitute equation 5.11 here in equation 5.10, can have Rg is equal to the weight of the vehicle times the tangent of theta g, and since this is very small, then Rg is equal to W times tan theta g can be equivalent to the vertical rise per some specified horizontal distance in percent. And last but not the least, resistance is the inertia, MA. Now, this is the tendency of the vehicle to resist the acceleration here because of the inclination. Inertia is the force required to cause a vehicle to move along a curved path, and it's actually a function of the degree of the curvature and the speed of the vehicle. The power requirements required to overcome the various resistance for propulsion and not for transmission, power, steering, etc. Okay, so the power requirement is equal to the resistance times the velocity in meters per second. Now, let's look at an example. This is an example from the book of Mannering and Washburn in 2014. The details are in the reference list at the end of this presentation.